All right, 2.4, comparing interest types and estimating doubling time. So at this point, your job would have been to fill out and complete the notes. Now, you are actually able to do these calculations alone without having to just straight up copy what I have down here in the notes. And hopefully you attempted to do that. But our first part of the notes that we are tackling is to compare how simple interest compares with compound interest. Now, how we're doing that is by looking at an example and seeing what interest we make, or really our final accumulated amount for each investment type when we invest the exact same amount of money into both investment types and they have the exact same interest rate. The only difference here being is that one is simple interest and one is compound interest compounded monthly. Now, you'll notice that in these calculations that we did, we'll see that our compound interest starts off already a little bit better than our simple interest, but nothing too major. Having $1.16 more isn't the biggest deal. But as we go on, we'll notice that the difference between the two of those grows. Right? We start off with a difference of $1.16, and we end up with a difference of $20.90. So that difference, that amount that we are making, is increasingly higher if we have left our money in the investment that earns compound interest. Now, this is pretty cool, and you might think it's cool, you might not, but I think it's pretty cool. And one thing that we can take a look is how to compare these graphically as well. If we noticed from the previous example on the previous page there, our simple interest, every single time the interest went up by $50, right? So we started off at 1,000, we get 1,050, we get 1,100, 1,150, 1,200, because every single time our simple interest is only earned on the original principal. And because the principal is consistent, the interest we earn is consistent. So we'll notice that the graph is linear. Now, if we're looking at compound interest, right, we notice that it grew, but not consistently, right? We started by, in the first year, growing by $1.16 total, whereas in the fourth year, we grew by 20-some dollars total. So we'll notice that the green line that represents compound interest here in my notes is not only kind of higher than that red line representing my simple interest, but also that it's not linear. There is some sort of exponential curve to it. And I've graphed both of these on Desmos just so that we can confirm what's going on here. So the graph that I just popped on here is our simple interest graph. We can see that this is a linear graph, and I've put on 4 horizontal lines just so we can see the value of that graph at X is 1, 2, 3, and 4, with X representing my time and my Y representing my accumulated amount. And that does match up with what we have calculated. Now, I'm going to take away that red line, and I'm going to add in this blue kind of graph. And I should also see something very similar to the values that we've calculated. Obviously, Desmos doesn't understand that we're talking about money, so we can see that there's a third decimal place. But if we round out our values, we should notice that they should be the same. Now, I'm going to take away these vertical lines because I don't really care about the exact value of my investment for my compound and simple interest. I was just showing you that they are identical as if we calculated them using our simple interest formula, or TVM. But what I am interested in is showing both of those two graphs, the blue representing compound interest, the red representing simple interest, and just seeing what happens over time. So if I change, instead of looking at my time span being to 4 years, let's say I change it to 25 years. I'll notice that as time goes on, my blue line skyrockets up. It is an exponential curve. So it's growing at an exponential rate, which if we take a look at x of 20, if I had invested in both of these investments for 20 years, I will notice that in 20 years, my simple interest an investment will have a total value of $2,000, whereas in my compound interest, I will have $2,712.64, which is now a significant difference. So simple interest, yeah, it doesn't make a big difference in the short term, but in the long term can be huge. And so that is what we were hoping to kind of get across in the big picture thoughts when comparing the two of these investment types and the interest types. Here are some advantages and disadvantages. So realistically, compound interest is the best for most of the investments and loans we will use in our lives. The one and only time that simple interest is good and compound interest is less good is this. When we have a loan, and it's a sizable loan, and we are not able to start paying it off right away. Because as we saw, if we have compound interest on a loan and we're not making any payments, that interest will skyrocket. It will grow exponentially. But at a point where I'm owing money and I can't pay it off right away so that it can go down, well, I don't mind an incremental increase of what I have to owe, but I rather it not grow at such an exponential rate. Growing in a linear rate is kind of the better option here. So, for example, this could be a loan that you take out, let's say for a student loan. And oftentimes banks understand that when you have a student loan, you don't have the funds to pay it back right away because oftentimes, depending what program you're in, you might not have enough time to also have a job. So if you take out a student loan, the banks understand that in the time it takes for you to finish your degree or program or diploma or whatever you are doing, you're not going to be making payments off that loan, but you still should be being charged interest. Now, depending on who you bank with, the bank might say, you know what, it's a student loan, I'm not going to charge you interest until you graduate. But it's also possible that they say, you know what, we are going to charge you interest, but it will be simple interest for the first 5 years, and then it'll be compound interest once you're able to start making payments. Because once we're starting to be able to make payments on those loans, compound interest tends to be the better option. Simple interest is only good for loans that are accumulating interest in which you're not able to start making payments on right away. All right, and the last thing that we kind of talk about in this set of notes is estimating the amount of time it'll take for an investment to double. This is called the rule of 72, mostly because there's a 72 in that formula. Okay. In this formula, we remember that T is the doubling time in years that it is estimated to double within. I is the interest rate expressed as a percent. Otherwise, the formula is pretty simplistic. It works best if we have an investment that is compounded annually, but it'll also work if we have an investment compounded monthly or daily or semi-weekly. Any of those options will still allow us to make an estimate for. It's just the estimate's going to be less accurate. Now, a lot of the times, we aren't interested in the nitty-gritty specifics. We want a general amount of time to consider having our money in some sort of investment for it to double. So if I invest $500 right now, today, how long will it take me to have that investment turn into $1,000? Now you'll notice that in the formula, there is no place for amount of money. Because it really doesn't matter how much money I've had originally. All I care about is how long it'll take to be twice as much. So there's no place for the amount of money that I have in the formula because it really doesn't actually make a difference. So if I'm looking at these examples, and I'm just going to pinpoint this one here. If I have an interest rate of 4%, it's going to take approximately 18 years for my investment to double. So if I put in $100 in 18 years, I should have $200. If I put in $5 million, then in 18 years, I should have $10 million. So the amount that I've invested isn't really a big deal. It just tells me the amount of time roughly it'll take that investment to double. So sometimes when we give you the value of an investment, it can be useless information. But sometimes, like in example 4 that we tackled here, it can talk about, well, if I start off with 5,000 and I want to end up with 40,000, I want to do that same estimation. But 5,000 to 40,000 isn't a double, right? 5,000 doubled is 10,000. So I can use the initial amount and my end goal, like this 40,000 here we have in part C, to figure out how many times it is doubling. The only estimation tool that we have in this unit, in this financial part of the course, is the rule of 72. So there will be some amount of doubling that will need to take place for you to get to the initial amount, to the final amount, if you are estimating an amount of time for it to reach that end result. Key tips here is, I always like writing out what the doubling looks like, because year after year there's students who go, okay, 5,000 doubled is 10,000. So I've increased by 5,000. So the next doubling will be 15,000. And the next double will be 20,000. But that's not true. I need to double with what I start off at every single time. So I have 5,000, I've doubled, I end up with 10,000. Now I get a fresh start. I have 10,000 in the bank. How long will it take for it to double? Well, we know that it'll take 24 years. So from 10,000 to turn into 20,000, it'll take an additional 24 years. So that is the one time that having the amount of money in the question can be useful to you. And that's it. So hopefully the notes did make sense, and hopefully this recap kind of helped in what we're doing. There is practice that follows, not a whole ton of it. Just one thing I will point out in the practice. So for example, question 3. Here I see estimate how soon Alexa could buy the motorcycle. As soon as I see estimate, I'm looking at a length of time. I'm looking at that rule of 72, which shouldn't be a surprise. But when it says verify your estimate, that just means use your TVM, figure out the actual amount of time it will take, and see if my estimate is fairly close to that end value. So that is what it means by verify. So estimate is rule of 72. And to verify that, I'm using TVM. I'm going to be solving for n. And remember, n refers to the number of payments. In this case, if we're not making payments, n will also refer to the number of years. But we can use TVM to verify that estimate. Figure out the exact, down to the decimal amount of time it'll take for that investment to double. All right, that's it. Have a good rest of your day, and hopefully I will see you tomorrow.